Dooby 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 doo, dooby 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 doo, dooby 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 doo. Hey, we've got sound, we've got vision. Yeah, we've got all of those good little things. And we've got a stream. Okay. Collision systems, huh? Really? Okay. Collision systems, yeah. We're rounding up. And I was thinking about the things that I missed during the series that we've been doing, series of streams. And I thought I'd round up with the last subject that I'd really missed and hadn't talked about too much. Collision systems. Because, yeah, we did do a detect collision on an axis-aligned bounding box. Very small detect collision function. Alright. Fair enough. Things don't look too bad. So, axis-aligned bounding box, huh? So, really, the only thing that I've covered is AA, BB. So, what does that involve? Let's think about it. If you want to create a game, what are you looking for? You're looking for speed. Speed of execution of your program. So that's why I've been keeping everything so simple. Trying to simplify everything down to boiling everything down to its simplest form. All the way through the series I've been doing that. And we've got this AABB thingy. And if we'll look at it, we have to detect the right hand side, the left hand side, the bottom and the top. So it's a square. It works really well with squares. It didn't do quite what we expected, but it really works well with squares. Something else that works a bit better than this, well, maybe, because we'd never tested it, is what happens if we replace the bounding box with just a circle. What happens here if we just go for, I'm going to call it a sphere actually, because it is, yeah. A sphere. In 2D that's a circle, in 3D it's a sphere. It's exactly the same calculation. And this is the thing that I hadn't mentioned. I apologise for my spelling, but hey ho, I'm having a great day with reading. So that's got 4 How many has this got? Yeah. Why is that? Because a sphere can be defined as position and radius. So you've got a single position point and you've got a single radius point. And this sides to a box. hold on a minute. If you go 3D instead of 2D, that goes up to 6, doesn't it? Because of 6 faces. But this doesn't move. There are advantages and disadvantages to both. If you want accuracy, AABB is the way. If you want generalized and speed, sphere is probably the way. One of the disadvantages with the sphere, sorry, the AABB, the bounding box, we can actually see it because it's in our program. I was lucky enough to get it to do its strange thing. So if you watch very carefully as we run this, the first time it hits the bat, I've got it all set up, I hope. Let's see if this will work. So the first time it hits the bat, crunch, it grabs it. Yeah. And this is due to the way that the program determines the collision and how we resolve the collision. So it's the resolver that's wrong. As you can see, it went all the way through the bat there. Yeah, and the bat does move. So you can cause yourself problems here with this grabbing. It grabs hold of it. And that's due to the shape. What is happening with the AABB? The corners are getting stuck inside the object as we calculate its next movement. It stays within, so calculating movement frame by frame. So if it doesn't get outside of the collision within the next frame, it still counts as a collision, and it keeps vibrating within the collision object, and it looks as though it grabs it and it goes straight, but it doesn't. It's actually waggling up and down, or whatever, side to side. Only by a couple of pixels. So that highlights one of the disadvantages of the axis-aligned bounding box. Does the sphere fix that? Not really. But it does get rid of the corners. You're actually calculating over a smaller size because the sphere fits inside the box rather than going outside. So you're actually doing a lot less work for exactly the same thing. Oh yes, there is a third one, which is the one that I probably will be exploring. I'm just going to call it tiles, and it's OneCalc. So it's the same as Sphere, but it's more simplistic and has none of the realistic aspects of the other two. And basically, all you say is one of these tiles is you can't go into it. It's solid, you can't move there. So if you try to move there, it just says no, and you don't move. And that cuts out the resolver. And it's the resolver that's causing the problem, not what you choose here. And each program that you write has a different resolver because of that, except for tiles, which is a can or can't move. It's binary. So this is just binary. Can I? Can't I move? So that's it's. I think tiles is probably the most simplistic version of collision. The sphere is the next one up, because then you have to write a resolver to resolve how you want the collision to react. And then AABB is the most complex. It's got the most calculations, and you've got to account more in the resolution of your collision and how you resolve it. So AABB probably wasn't the best to go for the example that we did. Interesting. Let's look at some code on the sphere. So that's AABB collision. I'm just going to pop in another file. This is a simplistic setup, isn't it? Alright. Oh, don't do that. I'm just going to pop up a sphere RS. Zen mode. Mod physics. Okay. Where's physics? There it is. So we'd have a public mod. And that's sphere, isn't it? Yeah. That's fine. Pop you in. So we can see what we did. Alright, looks okay. Oh, don't do that. Here we go. So it would be public struct. Basically, it's the same code, sort of. Alright, we would need an X and a Y for its position. And then all we need is our radius. And that's it. So already there's a difference. We will put the hash derive in, I think. Yeah. We'll add a default. Magic. And then it's just an implementation, isn't it? Lovely. Looking good already. Quite simple code. we would have a public function, new, and that would take in position X. Yeah. As an F32. Yeah, this will be alright. Position Y. Again, trying to keep everything as simple as possible. And a radius. Yeah, that'll be fine. I think I'm just going to put R there. Just to clean that up. Radius, again, F32. And this gives back self, doesn't it? Yep. So all we do is a sphere. And it's going to be X is position X. Y. Position Y. And already you can see that it's pretty straightforward. No problems there. Okay. Doesn't like it for some reason. Do 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 do. Cannot find struct variant. Or union type. Ah, yes. That's because we can't spell today. That's fine. I don't mind that. Okay, well, where's our implementation gone? Right, so that's your basic setup. So we would then use a public function to detect collision, which takes in and self, and it's a target, isn't it? Yeah, and a target. And that's just a sphere. Lovely. And it returns an F32. What we're returning? I think we can probably keep this the same. Yeah. I'm going to try and keep it as similar as possible. Collision. That's just going to equal 1.0. Some people are now starting to wonder why I've put that in. And I'll explain that. And that's just collision. Alright, so that's your basic setup done. Lovely. We can already see that the code looks a little smaller. Which isn't a bad thing. I don't think, anyway. Then we want this one to be detect collision. And then we just return the result, don't we? Okay. It's exactly the same code. Sort of. It can be possibly made easier. We have to move the target, because what we're doing here is we've got a vector of that magnitude. Mathematically speaking, how do I do this? Okay. So if we have two spheres, I'll do it this way. Yeah, this will do. So, yeah, that's about straight, isn't it? So if you have two spheres with the center points and their radius, we need to see whether these radiuses overlap or not. Well, in this case, they don't. But how do we calculate that? So we have to know whether the distance between the center points is less than the two radiuses. That's all we need. So it's D is less than, no, that's 2. R1 plus R2. And my can just go in the way. And that's the calculation. But how do we get D? Vectors don't work very well if they are floating around the X and Y axis. They work a lot better from the origin. To get to the origin, all we have to do is move that point there to there, and move that point there the same amount of distance towards there. Yeah. Or can we do it from here? Let's see, we can go negative, can't we? So I've just put it in the positive area, but there is the possibility that it could be out here, down here, or even down here. So we do have positives and negatives to worry about. Even if we move it to the origin, there still can be negatives and positives. Okay, R2 could be anywhere. Very, very simple mathematics, but when you come to vectors, it can all of a sudden just boggle your mind a little bit. Because people aren't used to working with vectors. Can I just do R1 minus R2? I can, can't I? Do I need to move it? This calculation is going to be a bit awkward. That distance there. The magnitude of the resulting vector is what we need to calculate. D. D is the crux, obviously. That's your control. We can use Pythagoras. We could use guesstimate. It's Pythagoras, isn't it? We're going to need x squared and y squared. So that gives us d squared, doesn't it? Yes, it does. Okay. So what we're calculating is the distance between the two. This is awkward. Is this more straightforward then? This is what I'm checking. Huh. Distance squared. Oh, an F64, huh? Why you giving me F64s? Interesting. Don't give me, don't do that to me. Why are you now upset? It's a return value. Alright, it's because of this. So you've got the target x, self x. So you've got self dot x minus, oh, it's going to square, so it's okay. It's going to come out positive. Oh, well, that's handy. Target x and you square that. Okay, we'll work it out to square u in a minute. And it's just plus. Well, yeah, we'll put it in brackets for a second or two. Self y minus, got to keep them the same way round, target y. Okay. Now we need to square that. Is it just dot square? How does Rust do these mathematical functions? Got an ABS. I didn't know we had that. We don't need it. We've got square root. Huh. So you don't give us square. All right. Yeah, okay, we'll do it the other way then. For now. So times it by itself. Better put that in brackets. Well, it doesn't matter. It's a multiplication, isn't it? Takes priority. Okay. I don't like doing it this way. So that gives us the correct value for distance squared. And we can leave it as distance squared. We don't need to square root it. So to detect the collision, it's an if statement. I'm just going to put an if statement in for now. It's the distance squared. Oh, now I've got to square everything else. Okay. It doesn't look very good, this. Is greater than or equal to self r for the radius plus the target's radius and we have to square it to match. What's wrong with you? Oh, it doesn't matter. So I've got all this square thingies going on. I'm going to check this out. I don't like it. Okay, and all we're doing is putting collision to -1. Yeah. Okay. So this is collision has occurred. And all we're doing is putting collision to equal -1. .0. Alright. That's the elongated way of doing it. Is that more simplistic? You don't need to square root it, by the way, because it doesn't matter whether it's all squared or not all squared. If you do square root it, will it need an absolute value? There's also a couple of mistakes that can be made on square rooting in F32, so I think we avoid that. That's absolutely fine, and that also increases its accuracy. Interesting. Interesting side effect. This squaring thing. Calculating x squared value. Let's see what it comes up with. See if we can simplify this code a little. Right, it's square, open brackets, and then x. Yeah, it's not a dot. It's a function. That's interesting. Alright. So that becomes square. Cannot find function square in this scope. Not found in this scope. Really? Oh, using a custom function. Okay. Using the multiplication operator. Powy method. x.powy2. I see. I wouldn't have guessed that. Huh. So what you're telling me is that there is a dot powy. Yeah, there is. And that just asks for a thing. Okay. Huh. It doesn't mind that. Alright, so that gets rid of the U. So simplifying things down now. Alright. Oh. Dot powy 2. Okay. That's okay there. Take that out. Dot powy 2. Oh, it's powf. Just to the power floating point. Okay. Maybe not. Powy. Okay. To the power of 2. Yeah. Alright, I'm slightly more agreement with that. One, two, three, return. 1, 2, 3, 4, return. We've actually got an extra instruction in there. Because we have to calculate the distance. It also makes more sense to reverse this. Yeah. So that is less than or equal to the distance squared. Right. That makes more sense in my head. Just to swap it around, make it read better. So if the two radiuses squared are less than the distance between them squared, a collision has occurred. Yes. That seems correct. Interesting. Which one is faster? Which detect collision is faster? And the answer is this one. The sphere is faster because we don't have 1, 2, 3, 4 logical statements in there. We only have the one. So we lose 3 there, we gain 1 instruction here. So we've actually halved the number of calculations within the function itself at the processor, at the CPU stage. It will run twice as fast? Probably, yeah. We can't take the if statement out because we're using -1 and 1. Let's just address that a second. Why am I using 1 and -1 and not true and false? Boolean true and false. Simple answer. 1 and -1 are more useful to us. True and false return values from this function will mean that we will need an extra if statement in our main program to decide what to do. 1 and -1, well, 1 times anything is whatever the anything started as. -1, however, times something reverses the something, mathematically speaking. So 1 and -1 are actually better values to return. It cancels out an if statement later on and reduces the amount of calculations we need to do just for this stage of collision. So the code is pretty straightforward. It's that PoE times 2 thingy that's going to catch people out, I think. The squared bit, it's Pythagoras. So x squared plus y squared equals the hypotenuse squared. It's that thingy. I tried to keep it as simple as possible without doing anything strange in here. Is that good enough? That calculation in itself is called a magnitude for a vector. Also, which would be in a maths library if we had written one. Which we haven't. I've been keeping away from the maths. It's usually the first thing I write when I'm doing libraries. Yeah. That would work. Interestingly enough. And it's exactly the same collision detection as on the left-hand side for the AA bounding box, with the corners chopped off. Interestingly. Is it better? Test it out. Is the answer. Give it a good testing. See what happens. Yeah, it could work better. It might. It's easier to resolve because we haven't really put a great resolver in. think we did one line of resolution, which is just reverse the direction, X or Y, depending on which side hit. Which side hit? Well, we didn't really tell from this one, so it's the same code. Can we just plug that in? There's our collisions. Don't think we put anything in there. No, we didn't. Here's our application. It will be the ball that we did. So we made a ball bounding box, a bat bounding box, and we had the ball velocity. So we set up the bounding boxes. Okay. We check the collision, and then we resolved the movement. Which, yeah, we just times. This is the -1 business. The result being 1 or -1 means we just get away with a single calculation for the resolution. If you put true and false in, you then have to put if true, and that turns into then a -1. So why do it that way? You got an if statement then. Which can be avoided, obviously, because I've avoided it. We could try plugging it in. How can we do that? Well, the velocity doesn't change. What changes is that line and that line. We really should now. Yeah, I think we're going to put sphere in front of that to differentiate the two. This pulls in a rectangle, that's fine. This is slightly more complicated than I wanted it to be. Okay. One of the things that's different about this is the original data isn't correct. The original data gives us a top left-hand corner of the rectangle. Huh. That's interesting. So we need to come back by half width and half height. Okay. All right. Just messing. I think I can keep that. Okay. Yeah, okay. I'm not too bothered about that bit. Yeah, we're just taking the Y there. That's interesting. Hmm. Yeah, this isn't, it's not straightforward. I think I might leave it. What you're really doing is you're just creating a sphere. You then have to get the center of the sphere into the XY, and the radius is either half X or half Y, assuming that it's a square. So this doesn't work for... that was it. That's why I got this thing. God damn it. Brain mashed. Where are we? We're in ball. What's going on here? I've got physics, AAB, and sphere. We're in reds, that's why. Okay, no, this won't work. Absolutely won't work. Not with the way I've just done it. Why won't it work? Because the bat is not a square. So if you want to replace your AABB, you've got to deal with squares, really. Rectangles become dodgy. So how do you deal with rectangles? So that's the limitation of the sphere. That's why I didn't use it. What you have to do with rectangles is split it down into 3 parts. And if you're playing a first-person shooter game, that's exactly what they do. They have a cylinder with a ball at the top and a ball at the bottom. A sphere at the top and a sphere at the bottom is the shape that they use. So that's also an option. I don't know what you would call it, but it's a shape that looks more like that. And then you've got the top and the bottom and the ground there. So it's a sphere, 2 spheres, and then in this case it's usually 2 rectangles. So you've actually got another sphere, so you've got 4 spheres, which funnily enough is quicker than the 6 sides to a box. Sorry, 6 sides to a cube. It's the same in 2 dimensions, you've still got 4 calcs. I think it's actually slightly slower in 2 dimensions if you use that, so you wouldn't, would you? You just use a sphere and squares. So if you wanted a rectangle in 2D, that's 3D. In 2D, you probably split your rectangle into 2 parts. Probably. You'd make it up as squares and do it that way. How you put all of this together is up to you, really. At the end of the day, what works best? No idea. All depends on your game. For the bat and ball that we've done, we'll probably need another one. Probably. To get a decent sized bat. So what you do is you call your detection for each of those spheres. So you're doing 3 runs through your detector. That's okay. That's not usually too bad because your detectors are usually very, very small code-wise. Yeah, I think I'd go down that route if you're going to test it on the simplistic program that I've put forward here. I think I'll go with 3. Yeah, I think that makes sense. Although we've got, so that would make your bat to 375. You could keep them all the same sizes, and if you standardized your data, you can go back down to 50 here. So you can standardize that, but yeah, this isn't a square either. What you would do is you pick a square size and go with square sizes. So you go 50 by 50 by 50 by 150 and use 3 squares for that. Yeah, that all makes sense. Or multiples thereof, depending on the scaling. I mean, you can always scale though. Probably go for 100 by 100 pixels there. Depending on the look and the feel of it. This data, I've made it awkward for myself to swap over. As long as you're using multiples, you'll be fine. Actually, the bat doesn't have to. Yeah, as long as you use squares, you'll be fine. I think that's one of the problems that we've got when on our resolver, is that these aren't squares. I never really thought about it that way. So your initial data should fit your physics system, and I never even thought about it at the beginning when just throwing in the data. Now I've thought about it, yeah, that makes more sense. So if we corrected our data, our AABB wouldn't be as bad. Huh. Wow. That's something for future me to think about. Okay. So initial data matters. Or your data set matters. That's really cool. So if I was to rewrite this game that, well, not game, but the basis for a game, if I was to write this again, you see, this is just off the cuff writing of a simple basic foundation for a game. But now I've thought about the physics and the collision system, I can see that we can alter our initial concepts for this to make things work better. And that's really interesting. So the design of the game itself, at the foundation level, matters. I mean, I don't think we could just slot in the circles for collisions and get everything to work perfectly. I think we can get things to work a lot better. Standardizing our data in some way would make it even easier. And of course, when we go to a tile-based idea, which is binary, that's automatically done because a tile is a standard size. So we've done things backwards, haven't we? A little bit. If we'd started off with tiles, we could have then gone on to the sphere and then onto the AABB, and we would have got a lot, well, we would have kept the simplicity, but our systems would be better. So the choices that I made during the demo weren't the best choices, were they? There you go. I've called myself out. That's fantastic. Alright, tile-based. Tile-based is a lot simpler. Because what we've got is a grid. We'll put an extra one in. So what we use is a grid. And each tile, so this is a single tile, each square is a single tile, and you usually do make them square, but this can hold data. You got your row and your columns. So you can actually attach data to a tile. So you would have a struct, if we were doing C, which we're not. You'd probably have a struct tile, and that would hold data. It would have a position, Would you call it solid or something? You wouldn't need its size because that would be standardized. That would be a set size, that would be a constant. Yeah, okay. You would need solid or non-solid. Yeah, all you would do is flag it as solid. Something like that, maybe. Yeah. So if it was solid, you couldn't enter that square. So it doesn't matter which direction you try and enter the square from. If the square says it's solid, then you just don't move. And that would be bool. That would be true or false. That's the most simple system that you can invent, really. Yeah. I think that's it's the same kind of amount of data as the sphere. So it's basically a copy of the sphere with an XY and then solidity, or whatever you want to call it. Think of a better name than that. But it's the same code. To be honest, if not simpler. You'd have your target. You could have your tile number. Does that matter? Row and column will do fine. So you'd have your same variable. You wouldn't need that. And all your detection is if the target square, you don't even really need self, do you? That's interesting. Because all you're really doing is checking the target square or the target tile. So you wouldn't have any physics at all. This wouldn't exist. It would all be incorporated within the tile information. So all you do is check the tile to see whether you can move there using an if tile dot solid, and if it's true you just put a collision marker in. So it's just if tile dot solid. God, that makes it so simple. Wow. I'm going to enjoy doing that one because it takes the whole of the physics idea and throws it in the bin. Yeah, alright, I'm okay with that then. So this can be held within the structure of the tile itself. So no physics system. that's the bonus to it, is that you completely remove the physics system. You keep everything contained within the structure of the tile, and all you do is check whether you can move into the tile, yes or no. You might add an extra data point to your player saying can move, but there's no real point. I don't even think of doing that. I think you can keep it pure code, just with that one extra flag, just using a single flag for the whole thing. So data wise, minimized as well. Huh. The only thing you've got to watch out for is this row and columns thing, because it reverses. That's your Y position, and that's your X position. X goes down, Y goes across. And it's always confusing when you start using grids, because everything reverses on your X's and Y's. But we found that with tables, didn't we? So we're using the table idea, and that's on purpose. Back from a number of streams ago, we set up some tables for data. Well, that's interesting. Now we've got a grid, we could just use a table for a map. That's going to get very interesting. I'm intrigued by all of that to see how it develops. We can't really do much with it at the moment as we have no graphics. So testing anything is gonna be a little dodgy, because we won't be able to see anything. That's a shame. I guess that brings me to the last part of this little thought session. I mean, this is just a thought experiment. It's nothing massive. So thought-wise, if we get ourselves a minimalistic graphics system, which I'm hoping to devise over the next month or so, I'm trying to think of an easy way of doing the graphics, and there is no easy solution to graphics, there never is. But I need to keep it as simple as possible to fit in with the kinds of things that I've been doing. So that's going to take a little bit of work, unfortunately. I've got to take the whole of OpenGL and simplify and boil it down into simple instructions. The tile part, we've just realised, boils down to one bool, which is amazing. Absolutely amazing. That's fine. We can do that. Amount of information I can put in a table. I'll think about that separately. But the OpenGL part of it, due to the way things fit together in computer science, is slightly overcomplicated in parts. And if I can simplify that down, I'll do a special series on it. But it's going to take me a few weeks to work out whether I can do that or not. It needs a bit of experimentation. Excellent. I think we've got a way forward to complete the project, if I can get the OpenGL to work. I mean, getting it to work, well, yeah, I can do that. That's not the problem. If I can get it to work in a simplistic way. which means probably using OpenGL 1.1, which, if I remember rightly, has direct draw incorporated into it from memory. Alright. So there's all my thoughts on collision systems. I've got a feeling we're going for tiles this time, so that it can be expanded on with a physics system on top later if I want to go freeform. So tiles is restrictive in that you can only move from tile to tile, whereas spheres and bounding boxes, as you can see, are freescape. You can move anywhere to any point or pixel. Yeah, I think I've covered most of the things that I really want to cover. This is how I do my research, by the way. If anybody was ever wondering, what I do is I have a black, some kind of drawing tool, and I just sketch my way through things and find out what's what goes where, what affects what. I'm gonna have to come up with, yeah, we will have to come up with different data, but we'll be doing that anyway because it's tile based. That's fine. Awesome sauce. I hope that was informative. And if you want to do any of the coding or anything like that, I think we've got enough. I've put enough code out there now for people to be comfortable enough to experiment and try things out for themselves. Just remember, keep it simple. Give it a kiss. There's no harm in simple programming. In fact, if you look at crates that have been issued out, you look at the kind of code that are in those crates, you'll find a lot of the time it's quite simple. And the simpler the better. One of the things I have realised from experience, though, this kind of thing is not necessarily bad. This if statements. Now, I try and avoid if statements, but they're not necessarily bad. When you compile your program, the compiler will look at your if statements and say, I can do better than that, and might alter the code totally. Factoring out some of the complexity. I don't like relying on the compiler, though. I usually like to remove it myself, then I know what the compiler's going to think. I'm not trying to help the compiler out. I'm trying to help myself by understanding what the compiler's going to do without having to look at the assembly code to find out what it did do. Working that out. When it generates the assembly code, I've got a feeling that that gets taken out. Probably will be actually in this. This is actually quite fast. Alright. I am happy with this idea. I'm just going to put a sphere introduced. Yeah, okay. G. Okay, there we go. Alright, so we've only got changes on dusk. That's good. Okay. Sphere collision. Basic. Yeah. I'll pop that in. And I'll sync it up so you've got the code up on GitHub if you want it. So that's up on GitHub. Fine. I'm happy with that. So it looks like we've got, again, that went a bit smoother than expected. It's not the best code, but it's simple enough for the kind of thing that I want to present. I wanted to show its simplicity, and I think that's getting there. Does that code work? Probably. To some point or other. I think we'll test out differently later on when I write it properly. But at least now we've got a version of it. Okay. Lovely. Magic. So we've finished our Windows 32 API as far as we can. So what I'll be looking at also is, can we do this, or are we going to go and play a game on Sunday? I think I'm going to play a game on Sunday. Rather than put this together at this stage, I think I'll wait for the graphics before putting this together. We've got nearly everything we need. Just the graphics to go. Alright. That's fine. Okay. Don't do it yet. Just don't do it yet. Because it's all going to fall to pieces at that point, and there'll be a lot of work to do probably. I don't think everything's just going to fit together very neatly at all. Things don't usually work that way. So, in the meantime, I'd like to thank you for popping by. Just a short chatty bit for our Thursday session here. All about collision systems and the different possibilities that you could entertain, and roughly how they all work. Sort of. But to give you a basic understanding of the differences and how we can use them in the future. And hopefully we will. We'll use all of them in the future, and hopefully we'll use them correctly. So in the meantime, take care, and above all, have fun.